The next section in Unit 2 discusses area models. Area models, in my opinion, are best for modeling theoretical probability. Of course, you're not unable to model experimental probability. It just becomes more and more difficult. First thing you want to do is start with a rectangle, a fairly good size rectangle based on however many events you have. If you have more events, the bigger the rectangle you have, the better you'll be able to model this probability with area model. And then you're going to divide the area of the rectangle or the multiple rectangles. After you start dividing it, you have more and more rectangles. You're going to divide the area into sections that are equal to their corresponding probabilities. So if you have two events and it's theoretical, each event is 50% probability. So you're going to take the area and divide whichever rectangle or rectangles you have, and you can divide them in half. So here to demonstrate a theoretical area model, we have three events. What I'm going to try to do is demonstrate not only the dividing of this area into smaller sections of area that represent probabilities, but I'm also going to try to label it clearly so you can understand and see how difficult this can get the more complex or the more in-depth you become with this topic. Three events: flipping a coin. Flipping a coin, we have heads or tails. That happens 50% for either one. So we do everything we can to divide this rectangle in half, 50%, and then we have heads or tails. Of course, the space you have dictates how long your labels are. So if I had more space, or if I decided to write sideways, I could write the whole word for heads. And notice that that division went left to right. Okay? The second one, so we got this flipping a coin modeled here. The second one, drawing four potential names. So we have to try to divide this evenly into four spaces. Now, I don't think those are exactly even. However, you have a ruler. If you want to fixate upon precise measurements, you can always have the kids do everything they can to measure it out and divide it by 4. However, but we're going to conceptualize this to be 4 equal divisions of this rectangle, and notice those divisions went vertically. So the second event went the opposite direction of the first event, and then those names, let's just say one name has a J, an M, an S, and a T. And so now we have 50% probability for heads or tails, and then 25% probability for drawing one of those names. To get J and heads, it's 50% times 25%. And so if you notice here, there's 8 equal boxes. So 100 divided by 8, I believe, is 12.5%. So that's how they would have to calculate the area in this type of situation. However, we're not quite done. And we have 4 sides of this rectangle, which means when you do 4 events, it's relatively easy. But once you get beyond 4 events, using an area model starts to get pretty tough. So now we have 3 colors. So we want to now divide. We have to divide this section here by 3 and this section by 3. Okay? So the 3 colors, let's say they are red, blue, and yellow. And so I've taken the outcome of flipping a coin of heads, all outcomes of picking a name, and I've divided those all by 3. So now I have to take the outcome of flipping a coin and getting tails, and I got to divide these all by 3 as well. And I have red, blue, and yellow. And now notice that each one of these boxes are conceptually identical in size and area because every division was supposed to be equivalent because it's theoretical. And so we have 1, 2, 3, 4 times 6. So we have 24 different possibilities, 24 combinations, which means the probability of each box is 1 divided by 24. Here we have a couple experimental probability events that we're going to try to put into an area model. In my opinion, it's best to make this all conceptual to where you're labeling everything, including the percentages this time, because if you try to do it exact, you'd have to use a measurement device. I would suggest centimeters, millimeters because of the base 10, and you can get 82% of all that, but once you start doing compound probabilities, that third event, you're starting to look at now some certain percent of another percent, and it starts to get a little bit difficult. So again, conceptually, this is going to make more sense as long as you put the percentages and label them in the correct places. So 82% for heads, 18% for tails. So earlier we went 50-50 because it was theoretical. Well, in this case now, we have 82%. So I'm claiming that this area is 82% of the original, and this is 18% of the original. So this is heads, this is tails. Notice I've labeled both the heads and tails and the percentages because I didn't measure it out. So I have to have some kind of number to help me gauge what I'm going to be doing in the future whenever I calculate probabilities. Red, the color red, now we got to go in an opposite direction. Now we don't have to go in an opposite direction, but it's going to make it easier to do that. So red is 25%, so that's approximately here. Blue is 37%, which is going to be bigger than this. However, 37 and 38%, those are pretty close to the same. So this is not going to be divided in half, but it's going to be very close to dividing this section here in half. So let's say right about there. We have 37% here for blue, and then 38% here for yellow. And now your compound probabilities, in order to get the area of this, we have to do 0.82 times 0.25. And then we'll get the area of this section right here. Same thing for each and every one of these. And that is area model.